physical modeling synthesis. So what the heck is that? In the context of electroacoustic music, physical modeling synthesis is one of these many new ways that we've heard about and that have been such great unparalleled successes in computer music research of bringing us new and exciting timbres to use in composition and live performance, whatever you want new and exciting timbres for. But the means of real-time control over these timbres has been lacking, I feel, in comparison to the great amount of the timbres themselves that have come around. So while things like tape music can make all these amazing new sound worlds, and computer music can do it even in real time to some extent, we don't have the link between performer and a lot of these sound-making capabilities that we now have. So my work was in some part trying to address this. The way I chose to go about it was taking this sort of overarching metaphor of a hand drum and trying to split it apart. So a hand drum is a physical object that makes a sound. And like all physical objects that make sound, its sound-making capabilities, the vibration of the membrane, the shape of it, the size of it, the acoustic cavity that generates the resonance, are all tied intimately to its capabilities as performance object. There's no way to separate the two. If you make a smaller drum, it's a smaller thing to perform on. But in theory, if you have a computer model where you can change all those attributes and a performance object of some kind that's very flexible and is as good as an acoustic instrument in terms of our perceptual ability to hear it being as good as an acoustic instrument, then you can make something that's like an acoustic instrument for all practical purposes, but through which you can decouple these two aspects of the object as sound producer and sound controller. So that was the idea, and the idea that supported the generation of this sound controller over here. So those are some questions that the research was hung on, but I think I've done a quick job of kind of laying them out here. The goals I wanted for my sound controlling instrument were that it be precise, durable, affordable in the long run, and easy to use. Instrument got in there at the beginning of that sentence, and that's kind of a funny word in this context because I've spent a while developing this instrument, this controller, the Soundplane, and everybody asks if they're not deeply familiar with this kind of work, well, what sounds does your instrument make? It's a natural question. And boy, where do you go with that one? I've gotten pretty good at saying, well, it's a computer controller, so it's not really an instrument then, and I think that we need some word that's in between controller and instrument for these things, which maybe doesn't exist yet. That's the best solution I can come up with, and I don't have the word yet, but I explain that my instrument just controls computer sounds. So it should be precise so the performer can repeatably perform on it and develop technique appropriate to the instrument. It should be durable so that I don't have to get woken up in the middle of the night when the performance isn't working, and the performer can happily stand behind it. Affordable because, and I think this is something that doesn't often enough make it into these discussions, but if you make something new, an instrument needs performers. Performers need composers, at least some of them do. And it's hard to, and composers need instrumentalists, and it's hard to kind of generate this sustaining web of activity without the instruments being out there. So while it's hard to make something new and have it be super affordable at the outset due just to matters of scale that are really hard to get around, that was definitely one of my goals. And ease of use was another interesting goal, which is something that, instrumentalists might think is really beside the point for an instrument. I mean, if you pick up a violin and ease of use it was clearly not designed for ease of use. It's designed for making amazing sounds. It's going to take you a long time with the violin before you make a sound somebody else would want to hear. But if you pick up something like this, there is at least the option of putting it into such a mode that it can immediately make sounds that you'd want to hear. Now, there's a whole spectrum of that from, you touch it once and it plays a recorded audio file to wherever you touch it, you have very, very tight control over the sounds that it's making. So the whole range of software that can explore those two sides, those two extremes of possibility in control, I hope will be developed farther and farther. So some work that's related to what I've done was actually started here in Victoria in approximately 2001. There's a company, Tactex, which I think is still here. What do you call that neighborhood where Tactex is?
I think they moved. They used to be down near the bridge downtown, on the other side of the bridge.
Oh.
I'm sure they're still there.
Okay. Well, in any case, they made this thing, the MTC Express, they called it. And this was really sort of a device that was very important in leading me to decide that I wanted to do this project because, I've been a person who plays around with audio gear and makes sounds using computers for a long time. And when I got a hold of one of these things, I thought, this is really an intriguing and interesting way of playing music. What it is a touch-sensitive surface, and you can see the scale of it there is, approximately 4 by 6 inches or something like that. And the sampling rate of it was about 100 hertz, which isn't really good enough for expressive performance. But what's amazing about this kind of an interface is that you can put multiple fingers down on it, that's possible with, say, an iPad now. But what's still not possible with an iPad is it detects the true force applied by each finger. So you can do something like, say, fade one sound in very gently with real-time control over it while you're fading another one out, or control the pitch of two things independently. So I had hooked this up with some Max MSP patches at the time and did a few shows with it, and I found that, I was just sort of bitten by the bug of playing music this way, I guess. So that in a sense, a long time ago, launched me on this path. Now, there's other related work out there. One of the things is the Continuum Fingerboard. How many people have seen this thing before in this group? Okay, it's a good kind of barometric question. So this is another attempt to solve a similar problem. It's in a more explicitly keyboard-oriented form factor. What it is a big box full of rods. And this, for scale, this thing is about the size of a grand piano keyboard. And it's 6 or 8 inches tall or something like that. It detects where you put each finger, up to as many fingers as you have, and where each finger is on the y-axis as well, and the z-axis as well. But you can't put 2 fingers at any given key, at any given X location, so to speak. The way it works is that it's got this network of springs under it and sensors and rods and sensors at each end. So if you put the finger down in the middle, each spring bends by about the same amount, and as you slide towards one or the other edge, the amount of force applied to each spring varies. So you get this, so it's this big box of tilting rods, and it feels a little like a big box of tilting rods too when you're playing it. On the other hand, it's a very groundbreaking instrument, and the kind of courage and intensity and vision it took to put something like this out, and I think Håkan has made something like 100 of them now in his basement lab. He just makes them by hand. I think is really incredible. There's another controller that was developed recently at CENMAT, the Electronic Music Laboratory in Berkeley, California, by David Wessel and associates there. And what this is a multi-touch controller, essentially made from a lot of different mouse pads. But what's different about this and any old collection of mouse pads is all the custom hardware that they used that takes data from all of these pads independently and very quickly and sends it to the computer as audio signals. So he's got this Max MSP software with objects that transmit all this data into MSP very transparently. And he uses it to do, the limitation is that only one finger can go on any one of these pads at once. But you can see how each one is more or less finger activity sized. And so it's again a pretty good approximation, but in a different way, of the kind of general purpose, multi-touch pressure sensitive surface that all these instruments seem to be homing in on.
Excuse me for interrupting, but if you slide your finger all the way across, is it clever about sort of gracefully moving from next?
David doesn't use it that way.
Really?
What he does is assigns a different sort of musical process to each pad.
So he really doesn't try to make it.
Yeah, he doesn't try and make it into one
Oh,
surface.
that's interesting.
Which is, in fact, we were talking about trying to figure out how to make mine more like his setup in a way, with different zones and things like that. So that brings us to the work done at UVic by Andy Schloss here and others on the audio input radio drum. And probably a lot of you have seen the drum. What I have is a picture here of its innards. The drum detects the position of the ends of two drumsticks in space above a pad that's approximately this big by this big in a spatial area, sort of really well suited to making a lot of performance gestures in. And though I was more interested in having a tabletop pressure sensitive controller, what really intrigued me about the radio drum and the work that had been done when I was coming here was, for one thing, the work that Ben Neville was doing to use the audio inputs of the computer to read the drum, because this lets, the first radio drums were made a long time ago by Max Matthews, also called the radio baton, and these instruments had external boxes that did all the processing and had the electronic pickups in them. So the external box would read the drum antennas and decide when triggers had been hit and so on. And there was a microcontroller in there running software to make all these decisions. And it worked well, but it's very inflexible. When you have something like that, it's hard to say, well, let's implement this other algorithm for detecting where the sticks are. That kind of thing takes a long time. So with the audio input drum, you can change the algorithms, all aspects of it in software very easily. Another thing I liked about it a lot was the fast sampling rate that using the audio hardware that's out there now allows. When Andy plays this thing now, it's very, very tightly coupled to his motions. And furthermore, the gestural signals that are made are really tightly coupled to the audio that's coming out using the same technology. So the whole feedback loop is really good. The radio drum is a capacitive sensor, and it uses the amount of an alternating current that is in each of these coils at the end of a drumstick. It transmits those from the drumsticks and picks them up at different antennas within the pad. And so based on the amount of signal transmitted, you can tell the distance between the two, because the distance drops off, the transmitted amplitude drops off with distance. And one of the neat things about this arrangement is that very close to the surface of the playing pad, because the distance drops off with an equation that has 1 over the distance in it somewhere, you get a lot of sensitivity really close to the surface. And so when I was thinking about a pressure sensitive surface, I thought, well, all the stuff I'm doing is close to the surface, so maybe I could use this technique somehow. That thinking led to this, which was a prototype of an 8x8 sensor designed along the lines of the audio input radio drum. So essentially what I was thinking when I was starting to design this was, well, you could make a surface sensor just out of the radio drum, in fact, without any new electronics if you wanted to. If you took the sticks and just kind of buried them under another sheet of foam or something, you'd have a two-point sensor where you press down on each one and it would tell you where you're pressing on the sides of the foam. But then I realized you don't need this multiple antennas setup that's in the base of the thing anymore. You can see where the radio drum has these four little subsystems at the corners of this diagram is each a separate amplifier that sends a separate audio signal to the computer. And why 4 of those are required is that they're determining the position of the things over the pad. But if you're using 2 coils glued to the pad, essentially, like I talked about, you don't need the position anymore. So what you can do is use an array of pickups that are fixed and an array of transmitters that are fixed, where each transmitter is being received by multiple pickups. So this is the drawing of what that ends up looking like. And I guess I'm going to shoot for just a little more size there. So this block to the right is the thing I just showed you with all the copper strips. To do the thesis work, 2 other components were required. An audio interface, 8x8, and a computer to do all the math. So the way it worked as a sensor is the computer tells the audio interface to send via these carrier strips, which are in this diagram the horizontal ones, but actually here they're the vertical ones. Over each carrier strip, a different frequency of sine wave. These range from about 6 kilohertz to 16 kilohertz, and those were picked just to work with the audio interface well, basically. Then there's a layer of foam under those flexible copper strips with the different frequencies radiating through them. And under that, there's a layer of perpendicular pickups, each of which crosses all of the carrier strips and goes back to the audio interface and back to the computer. So the computer reads those signals, and based on the mix of different amplitudes of the carriers that appears on each pickup, it's able to determine the distances between the copper strips, and then eventually the force that is applied to the surface. So that brings us to the artifact I have now after about 2 years of development, which is the Soundplane Model A. I'm calling it Model A because I'm hoping that I'll make models B and C someday if I survive long enough to do that. So what it is an instrument that approximates a continuous pressure sensing surface. And where the prototype was an 8x8, the Soundplane A over here is an 8x64 surface. So in the background here, I've been running the client application for the Soundplane, which we'll talk more about in a bit. I could calibrate that to see kind of where all the rest values are for the sensor. And then if I come along with my finger and I press on it a little bit, you see the increased amplitude when I press. And of course, if I press in 2 places, it produces a kind of pressure sensitive map of the whole surface. And this map is generated at 1,000 samples per second. One thing I like about the touch response is that it's able to detect a really wide range of performance gestures, from this very light sweeping I'm doing to a really heavy touch like that. So I like to call that encouraging effort, because a lot of computer music interfaces don't really encourage effort. They're a little thing that you poke at, and but we have all these great acoustic instruments that do encourage effort. So I'm interested in bringing more of that to the performance of computer sounds, if possible. Now, under what you're seeing here on the green lines is the actual data that's being made by the Soundplane, 8x64 junctions. But if you look at the surface of the instrument here, what you see is not 8x64, but 5x 5 by 32 sort of discrete keys that were overlaid over it. And what the keys are is twofold. On one hand, they're a way that I figured out of making a wood surface that's flexible. I really wanted the thing to be wood. When I tell people in 10 seconds what's the Soundplane, I say, what do I say again? I say, it's a computer interface for playing electronic sounds with the sensitivity and feel of an acoustic instrument. And that's really, in the feel part of it, I thought, what better than wood to play? But in making the wood surface, it took me a while to realize that wood is not elastic. You can make a thin sheet of wood and it'll be flexible, it'll bend, but if you press it in the middle, it won't allow you to make a single point like that. It will always look like a big tent covering the whole surface. So by backing the wood with a sheet of rubber and then laser cutting through the wood but not through the rubber, I was able to make a kind of articulated wood surface, which has these very fine kind of anti-fret lines in it that you can use to determine where you are. So the other part of that is I talked about two reasons for this layout of keys on what's otherwise a continuous surface. The other reason is that with something like this, a lot of people want a starting point. They don't want to kind of, here's your multi-touch continuous surface, tabula rasa, and now think of something to do on it. I think if you're making a new instrument, the people that want something infinitely flexible are going to figure out a way to make it infinitely flexible. But for acceptance of people who just want to start playing music a little more quickly, it's good to have a sort of suggestion about how to do that. So you can see with the Soundplane here, I've put a guitar-like fret markings on it. And I went through like 3 or 4 different ideas for how to do the fret markings. Eventually realized that the guitar had solved this problem really quite well, because you can visually orient yourself very quickly on these. It's obvious what's an octave and what's in between. And also the choice of the kind of ranks with respect to each other is still open-ended. So the first time I tried to put dots on this, I had sort of dots all over it that determine, what are the ratios between these multiple rows of notes. But obviously, as with guitars, everybody has a different idea what that might be. And with this instrument, they might just be different sounds. So this seemed like a good compromise. Although it's worth noting that it's pretty easy to make a new one of these surfaces with the computer-aided manufacturing process that I'm using. So if anyone's got, like I have one idea that's just a grid of hexagons, and if anybody's got other ideas they really, really want to see happen, they should let me know. So I have some technical stuff here and trade-offs and the kind of processor that was used and so on. I think those are questions that I'm happy to answer if anybody has questions about the particular details on a technical level. Obviously through the thesis, the process that I'm using is very transparent, I hope, and easily explained, and I think it's a fertile area for anybody that wants to experiment with making your own controllers. But I do want to talk about the software a little, because if you have something called an instrument that doesn't make sound but needs a computer to be used, software is really crucial. So the first level of software you're seeing, the software comes in layers. The first layer actually is just pure, is getting any kind of data from it at all to the computer over USB. So what we did is use this mode of USB called isochronous, meaning equally clocked, that's used for things like audio interfaces. And it means that the gestural data itself is capable of having very low jitter, which, like I talked about before with the radio drum, is a very, very important thing for a performance controller to have. So on top of that, we need to next calibrate the raw data we're getting. If you look at the raw data coming out of the controller, it looks like that. which is pretty interesting. Each carrier, which is a vertical column on the Soundplane, has a different amplitude because of things like the frequency response of the amplifiers and just the way that the materials inside the device attenuate different frequencies. So you can see it's symmetrical, which is pretty nice. And when you press on it, you see a range of motion on each one. It's not from the maximum to the minimum, as you might expect. It varies a little according to pressure. So what the calibration does is takes that range and scales it to a range of 0 to 1 across the board, like that. Next there is, this should not say taxal detection here, but it should say something like centroid detection. So I'm using this device, and obviously I want to know where my fingers are in X and Y a lot, as opposed to just the pressure that's applied. But the only data I have is the raw pressure. So what do? I take these, I look at this thing just essentially like a video image, and I try and determine what are the discrete lumps of pressure in this thing, and then I turn each of the discrete lumps into a position by adding up all the taxels, the junction readings that are around that position. Then I get the center of gravity of that. It's really the same equation as where an object will sit on your hand if you try and balance it. And then that determines where the center of this touch is. So,
I'm sorry to interrupt again, but is the noise that we see there, is that electromagnetic or just sort of, what is that?
yeah, that's RF noise.
RF,
And if you look at this is all the noise if you don't filter it.
Mm-hmm.
And this is with the little filtering being done so that you can actually play the thing.
Mm-hmm.
And it's worth noting that this software is a work in progress. I actually had a different I had a different surface on this before that wasn't as good to play. It had a sort of foam under, and now that we've nailed down the final composition of the surface, the software that calibrates it has to be changed. It's a little thinner and more noise comes through and things. So what I'm going to do is actually show a video of this thing working as well as it has ever worked, and then I'm going to invite people to play with it with the caveat that it's not working quite as well as it was a few weeks ago. But it's a work in progress. As long as I'm talking about that, I might say what else might be changed. The case is not quite final, and I want to really go with this nice instrument quality as much as possible. So hopefully we're going to get the bottom looking like it's made out of the same material as the rest, and kind of finish off these bits in here, and then make the software both as responsive and noise rejecting as possible. But what is done is this final surface and the computer brain, which I haven't talked about much, but was the bulk of the work for the last couple of years. Really the biggest job was taking this external audio interface that was used to run the prototype and designing our own audio interface that fits in this thing and has fairly high capabilities and can be powered over USB. So I don't mind, your question was a good one, but it did lead me somewhere. Now I'm not sure where I am.
Sorry.
It happens though.
Not to further derail you, but not to disturb your progression, but it would be fun to hear a little bit about the synthesizer too. I don't know if that's part of your talk.
I'm just about to get there. In fact, thanks for reminding me where I was.
Okay.
So you've got this layer of determining where you are on it, and then there's a few ways you can go with it in the software that we are going to ship with it in approximately 8 to 10 weeks when this thing is available. There's the first batch of 30 that we're making, and I could talk more about at the end how to get one if you're interested. But After this layer of software implemented by this app is done, you have touches with X, Y, and pressure for each of them. And so with that information, one thing you could do is send it to Max MSP, which we've seen used a little while ago. And that looks like a Soundplane Max patch. So this is a very simple synthesizer that just has a sort of sawtooth wave for each note that's detected. And I have to see, okay, this guy needs a little attention. Now, turn this back up. So I've got a simple mapping going on here of pressure to loudness. And X to pitch, obviously, with the same, and it's a fretless. It's a fretless mapping, so it's continuous. And then the Y in this case is mapped to a filter cutoff for each voice. So you can like, you know, so you can actually play the thing. It's pretty cool. So that's, and what comes out of Max is really sort of the continuous mode of operation. So out of each of these numbers, it's using open sound control to transfer the information to Max. And that's the way I'll keep doing it. In addition, there might be an object that just sits in Max, so you don't need this external application. It would be called Soundplane tilde or something, and signals would come directly out of it. But you can see I'm printing those here, or just printing the first one, I guess. And I get something that's obviously very continuous, but yet is something over which I have a fine positional control. So that's the Max end of things. And the other end of things is this synthesizer I've made. So when I was starting this project and finishing up the thesis, I thought, yeah, I've got this great idea for product, and a hardware engineer friend to work on it, and enough savings to finance the long time, 6 or 8 months that it's going to take me to finish this project, and it's really a great plan. So like a year and a half later, I was like, well, I really need to generate some income now if I don't want to get a job. So, but all along I had this idea of making the synthesizer that would go along with it, so that people who aren't Max MSP hackers would be able to just play something when they unwrap this and take it home. So that's what this is, and what I did with it is I also turned it into its own product. So you can go on our website now and get this synthesizer called Aalto, not for Soundplane, from us, and play with MIDI keyboards and things. So with the synthesizer, what I've done is a slightly different mapping, where I use the rows so you can hear each of them is on fourths right now, compared to the next one. And that's a very boring sound, but I've obviously got more interesting ones. This one's kind of doing an overblown flute thing using a waveguide, where you go from one key to the next, and you can kind of hear it start to speak before it's actually going into kind of full bloom there. And as you go from key to key, you can get some of these weird enharmonic things that make the waveguide speak with different overtones. It's pretty fun. So where are we at now? As I was saying, this thing is almost done, but not quite. I'm gonna have to take time and do a complete sort of rewrite of the calibration software, because I was using a technique that was good enough for my thesis with the original 8x8 thing, but it just didn't hold up with this more difficult problem. So I'm going to revisit that with better modeling software. And it's going to be a Macintosh-only thing for starters because of some weird technical details of communicating with Windows as opposed to the Mac over USB. It was a project that took much longer than I thought it would. 10K in 6 months or something was what I thought, and it's been about 4 times each of those so far. But I'm still on it, so that's good. And I think I'm getting close to something, an artifact that, if not perfectly nails, then at least, allows for the possibility of this idea that you can have a computer controller that is something like as sensitive as an acoustic instrument. So I hope that it's widely adopted by adventurous players and composers. So with that, I'll thank you and open it up for questions. And after that, trying it out, obviously.
I just had a kind of an observation. It seems like the calibration could almost switch that to tuning. Because those knobs, those calibrating knobs, could almost be on the instrument itself. And like I could see a musician playing with this thing and go like, oh shit, there's too much radio frequency interference, and I gotta alter it for that venue where you're playing in a noisy church as opposed to a perfect concert hall.
Yeah, certainly. There's a lot of knobs right now, and I hope there won't be as many. These are more for me trying to figure out, like you saw me tweaking on it to get it to behave a little better in this environment.
Of physical knobs.
Mm-hmm.
Like someone's, like this thing a guitar player, you see them playing a guitar and they're tuning as they're playing.
Oh yeah.
As their instrument warps and with the.
Yeah, I was trying to decide if I should put, obviously there's this big blank space here where you might think you put knobs or sliders, but the thing is, you can buy a box with knobs or sliders on it now for like nothing.
Right.
And everybody's got a different idea about what they might want to, so I decided to go with plain.
Has there been any, you must have, I'm sorry, I'm totally new to it, so I'm a bit fascinated, but have you done shows and stuff?
I haven't, because I'm still working on this thing, but what I didn't do is play the video of a bunch of people. I told you that it was working great a couple of weeks ago with the previous Surface. So I haven't, but here's a really interesting video of a bunch of people and their very first encounter with the Soundplane. And I like to see the variety of approaches, both by trained musicians and people who didn't approach it with any kind of musical skills, but yet made some pretty neat sounds on it.
Sounds like a 70s sci-fi
Do you want to make Wookiee noises with a new controller? Wow. Super organic. That's pretty.
Let's play a game. You chase me. How about that? Where are you at?
Alright. So obviously had to get that one in there. It's important.
What's durability wise? Like how, I mean, obviously you don't want to smash it over something, but I mean like, is there a point when I'm just going to put too much pressure and it's going to damage it?
I don't think so with your, like maybe with your elbow,
Yeah.
but
like if I like,
not with your fingers. In my experience, it will always snap back. That's one of the harder parts of the calibration software is, you know, after you move this thing, it comes back. I'm pressing on it about as hard as I could do without being in pain right now, and then it takes a little while to settle down, and you see that it's got a little history of the pressure in it. So part of the software is dynamically calibrating for that stuff.
is there a possibility of burn-in over time?
No, not really. I mean, to be precise about it, the elastic material, like if you put a weight, they have specs on that stuff, so you can read all about the elastic material, and it does squish over time if you really, you know, clamp it and like leave it there, but it's a pretty small amount, and then the calibration software will, you hit this button and it'll zero it out every time, essentially. So.
When you put the grid on it, I guess I'm trying to figure out how you were thinking about it as a musical interface.
Mm-hmm.
Putting the grid on it, especially like the fretboard markers, like kind of, it immediately sort of puts me in mind of like guitar fingerboard, or I mean just the divisions, a keyboard or something. I mean, in your own mind, do you think of it at all as something like it could ultimately, with zone detection, are you thinking of using it like a launch pad or like some sort of, you know, an array of buttons as well, or something that can track gestures? So if one were to, you know, move one's finger in a particular way across the board to track that gesture and map it to some control aspect that wasn't necessarily note related.
Mm-hmm. Yeah. Where do I start with that? Well, the markings are a sort of, so obviously it's surfaced with a lot of possibilities, and people have written these kinds of gestural interface routines. One thing I'm doing with this software, which is going to be open source, I don't know if I mentioned that, but it makes it easy for other people to use like things that have been written already. There's an interface called Tuio that a lot of people use to make, you know, you've seen those multi-touch camera surface kind of demos. There's a whole sort of standard that those things use so that one guy's demo can work with a different surface or vice versa. So I'm putting out that information, and hopefully that'll make it easy for people who want to do that kind of stuff with it. But I guess the kind of larger, I think your question is a really crucial one, is in like why did you, if I'm hearing you right, sort of why did I not restrict it, but why did I offer this strong suggestion of a particular way to use it? Maybe.
In a way, I mean, it was like, what's in your mind?
Well, for me, it's to kind of create a starting point that people will share. So it might be that you know, if you imagine music getting written for this thing, you could write music in graphical notation, and it's you know, it's gestures that control things and computer music pieces and what have you. But that's music for you know, the 1% or whatever, not to marginalize, but the probably smaller percentage of the music playing population that's interested in that as compared to playing notes and some temperament or other. Now, is that a mistake? Are the people interested in something like this really mostly interested in, you know, free-form playing and gestures? I'm not sure, but I'm guessing that offering this as a starting point is going to make it more widely approachable and not really restrict the use of it by other people. And there might be an option, though I'm not certain about this. I could have a grid on it that's as fine as that, and it would still make sense. So it wouldn't be the idea of a note grid anymore, but it would just be there for the mechanics of allowing the surface to move.
Thank you very much.
All right. Well, I'll also invite you're very welcome, and I'll also invite the tapping and whatnot.
We have food now for the next hour. We have food for you and drink, which we're going to bring in here, I think. But hang out, eat some food, and then the concert's at approximately 7 o'clock. Across the way in 037.
Turn it around. I've got like the world's smallest USB cable for some reason I grabbed this morning.
Where's the food?
Oh,
yeah, they left it in the hallway.
get in there.
Oh, so it's about $1,700. And what I'm doing is taking pre-orders for the first run of 30 that I'm making, and those are about half called for, half reserved. So not the price.
Between like point to counterpoint, like how you should use it on, like
Oh, that's right, I changed that. I did.
If they want to stay on.
How contiguous? Well, it's the data that you see on the grid is like exactly what's coming out of the box. You know, there's two grid lines for every one of those keys there, essentially. So you can tell where you are for each key really well. I'm putting that information out into the synthesizer here with an X output. So if I go from if I go on one key and then I change this knob that's coming from my DX output, I get a big pitch shift over each individual key as I go from left to right over it like that. This is good.
That's not bad.
It's about $1,700.
Continuum was a bunch of products.
Yeah, that's how it's done. It's interesting, like the louder you make the sound, the more sensitive it seems. Basically.
Holy.
Like that's doing something.